Those are
All right, so today we're doing section 15.8, which is spherical coordinates. Learning target. I can write a triple integral using spherical coordinates. If there was ever a time that you paid attention, today should be that day. This should be that time. Okay? All right? Danny, I'm looking at you. Hi. That's because even while I'm saying pay attention, he's still like off in his own little thing. So that's fine. All right. So please pay attention. Spherical coordinates aren't bad once you get them, but the getting of them can be a little, it's a minor, a tiny little mountain that you got to climb over. So. Yes, Tejas.
So when we were doing the triple integrals, we're also examining the z's, right? Or are we not graphing the z's?
I never graph the z's myself. Like I always just graph the region that I'm integrating over. Now with spherical, you're going to have to graph some cross sections. So in order to get things right, they're very different from anything else we've done. So that's okay. You'll be okay. So, okay. All right. Okay. So with your rectangular and polar coordinates, both of those systems were based on kind of the same premise, where you created in a plane that was either in the xy plane or parallel to the xy plane, you had a region that you were integrating over, and then you went up and down by z. Right, from that region. Now spherical coordinates change that quite dramatically. So spherical is its own like really fun, crazy universe. So here we go, stepping into spherical.
Whoa.
So the first thing that you might want to write down are how to relate spherical coordinates to x, y, and z. All right, so this symbol right here is pronounced rho, R-H-O, rho, or rho, but I just say rho. All right, this symbol right here is called phi, and then of course that's theta. Those are the three variables in spherical coordinates. So the three variables are rho, phi, and theta. So yeah, there's different ways that people write phi. Some people do a circle and a line. Some people do the squiggle thing. It doesn't. I don't care. As long as it looks remotely like a phi, that's fine. Please don't. All right. So x equals rho sine phi cosine theta. Y equals rho sine phi sine theta. Z equals rho cosine phi. X squared plus y squared plus z squared equals rho squared. And r equals rho sine phi. Now, which kind of helps you, if you know r equals rho sine phi, then you can get your x and y because x is r cosine theta, y is r sine theta, right? So as long as you know that r is rho sine phi, you kind of got the x and the y, right? So the z is a little different. So rho cosine. Now, the rho, the x squared plus y squared plus z squared equals rho squared, should give you a hint as to why these are called spherical coordinates. Because rho is the radius of a sphere, right? Right? Well, yeah.
What's the radius?
Okay. So anyway, now when we write, when we convert from rectangular to spherical, you know when we convert from rectangular to cylindrical, you got to put an r, d, z, dr, d theta. Well, when you convert from rectangular to spherical, you got to put a rho squared sine phi. D rho, d phi, d theta. Standard is d rho, d phi, d theta. I'm not going to make you convert, like rearrange the order of the units. We're always going to go d rho d phi d theta. Once you have this written down, and I know you don't know what rho, phi, and theta are yet. That's okay. Well, theta is the same, but you still might not be able to visualize yet. I'm going to show you in a picture, and then it'll be time for the dingle ball. All right.
What?
That's what I said.
I'm scared.
Guys, this is a dingle ball. Chill. It's like it's like in the Little Mermaid, but it's a dingle hopper.
By the way, I tend to love to use spherical anytime I have a cone or a sphere. The other shapes, if I have any other type of shape, I tend to stick with rectangular or cylindrical.
Zero.
Are we gonna like have questions that we have to use this on, or is it just gonna be like?
No, but there will be at least one question on your test where if you do it in spherical, it'll take you literally 14 seconds. And if you do it in any other type of coordinate system, it's going to take you, 10 minutes. So, huh? I would learn this. Yeah. Besides the fact that you're required to learn it.
Yeah.
Right? Okay. All right.
I would learn.
Okay, now can I scroll?
Yes.
No? Okay. All right. So, first of all, I have a note here. Please note the word usually. This is not always. If we use spherical to find a volume that's bounded by a cylinder, you end up having functions in there for your rho, and your phi. But most of the time, whenever you have like a cone or a sphere, both your theta and your phi end up usually being constants, which is nice. So, but it's just figuring out the constants that gets a little tricky. But usually theta and phi end up being constants, especially for cones and spheres. All right. However, sometimes there are other shapes that you might have to find volumes of using spherical coordinates. And I gave you a little hint on how to figure some things out. So I still haven't shown you what they are yet, but I'm just going to show you this first in case you want to write these down. Because it took me a while to kind of figure these out myself. So I kind of made them as a little guide for you guys. So last year, first semester, I didn't know any of this, so I didn't tell anybody anything. And we just basically said, do your best and send them on their way. So second semester, I kind of started nailing all this out and made a little snapshot of, okay, if you see this, remember it's this. If you see this, remember it's this. So anyway, it might be helpful to you, but you might not find it helpful at all. So I just want to get all the writing out of the way before I start really teaching you guys what's what. Yes, Dorsa.
So is A a constant?
All right, let's learn what spherical coordinates actually are. So first I'm going to show you using this image, and then I'm going to try to show you with an actual physical object. So the dingle ball. All right, so in spherical coordinates, this is your x, y, z plane, right? So theta is still theta. Theta has always been and always will be the angle formed with the positive x-axis. So theta always goes around this way. It's the angle formed with the positive x-axis. So if you had, in your xy plane, if you had a circle, your theta would go 0 to 2 pi, right? It's the angle formed with the positive. So theta hasn't changed. So you got comfort and theta hasn't changed. Now, in polar and cylindrical, r is the radius from the pole that is coming out, like it's coming out from the pole, but it's on the xy plane or parallel to the xy plane, right? So r is that radius coming out. So that's why when you have an r and a theta, it produces some point, but it's still on or parallel to the xy plane, right? So here's where spherical and then z is coming up straight up, right? Z comes straight up. All right. So say we're getting to this point right here. In traditional rectangular coordinates, you go out x, over y, up z. In cylindrical coordinates, you would go over theta, out r, up z. In spherical coordinates, so in spherical coordinates, rho is the distance from the origin to the point you're talking about. So it's like a radius always from the origin. Rho is measured from the origin, but it can go up or down like anywhere. So rho is distance from the origin to whatever point you're talking about. Theta is still theta, but phi is the angle with the positive z axis. So phi actually it's going to feel wrong for a while that, like, if I have an angle of pi 6, it's like this, where this is pi 6. So it's the angle with the positive z axis. All right? So what happens is, if I want to get to this point in spherical coordinates, so I have like the phi tells me how far down from z do I go. The rho tells me how far I go towards that point, and then the theta is what like turns me this way. Okay. So last year I cut up a dingle ball. I don't know what they're called. Okay. And I really destroyed it. Like, this is destroyed. I might cut up the colored one. Let me pause. All right. So we're going to set up, but do not evaluate 3 triple integrals. We're going to start with rectangular. We're going to do cylindrical. And then we're going to do spherical, all to generate the same thing. All right? So what are we going to generate? We're going to find the volume of the solid below x squared plus y squared equals 64, which is this lovely sphere of radius 8, and above the flat plane z equals 4. So what are you getting? You're essentially, like, if you think about, like, it's this space in here. So what you're really getting is the top of an ice cream cone. So z equals 4 is flat. It's parallel to the xy plane. And then you've got this dome part of the sphere that's being cut off by that plane. So it's like you're just finding the volume of just the ice cream that's on top of the cone. Okay? All right. So your first job on paper, and you can talk to each other if you need to, is to see if you can figure out how to find this volume using rectangular coordinates, x's, y's, and z's. All right? X's, y's, and z's. All right, so for our rectangular coordinates, so the z is the easiest part, right? The z, the lower, like, we're doing this dome area here, so the lower bound for our z is 4, and the upper bound for our z is the sphere. Whoops, oh, I didn't mean to actually hit that, but that's okay. Is the sphere solved for z, right? And it would just be the positive part, because you're only on the positive part of the sphere. All right, everyone comfortable with the z?
Yes.
So then we got to get the y. So I'm going to move this down so you can't see. So to get the y, so we've got to generate this circle right here. That's the region over which we're integrating. So if we think about this in the xy plane, so this circle is not, if you set z equal to 0, right? It's not x squared plus y squared equals 64, because that would be this circle down here where z is 0, right? We're not at z equals 0. We're at z equals 4. So you need to plug in a 4 for your z. And when you plug in a 4 for your z, you end up getting x squared plus y squared equals 48, right? So you solve for y, and you get y, this is the root of 48 minus x squared, and this, y equals, and this is y equals negative the root of 48 minus x squared.
I have a quick question about changing it so that like it's radius 4 instead of radius 8, where it's like the radius at the origin. So like, can we just have any surface that cuts that top of the cone off? So wouldn't that also like work?
What do you mean by any surface?
Like any surface that isolates the top of it so that you're integrating from that surface, which is where the circle is, to the top of the sphere.
So your question is like, could I use z equals 3 or z equals 2?
No, anything that where z. That makes sense. Never mind,
No, I want to, am I not understanding? Tell me, just try to say it again so that I can understand what you're saying. No, I don't think you're good, but I think you don't, I think you want us to move on. But I want to make sure that you understand that the only thing that generates this exact measured, dome is from 4 to the sphere. Because that's like the bottom boundary of this. I mean, the only other way to do it is if you move the whole sphere down, and you got to change the equation to move it down. Right? Okay. All right, and then your x. So your x is like this point and this point. So these points happen to be where y is 0. So your x ends up being negative root 48 to positive root 48. So anyway, so rectangular, when all is said and done, come back. There we go. So rectangular looks like this. So the volume would be negative root 48 to root 48, negative root 48 minus x squared to positive root 48 minus x squared, and then 4 to root 64 minus x squared minus y squared dz dy dx. All right. Now it's time to try the same thing in cylindrical, which shouldn't take very long because cylindrical and rectangular are pretty similar. The only difference is that instead of x and y, you're going to have an r theta to generate that circle, right? And then you got to rewrite your z's in terms of r's and or thetas. So for cylindrical, the z's, the only thing that changes with the z is still going to go from 4, but then this is going to be root 64 minus r squared, right? Okay. So then, but now we have, so that's our dz, and then, so to generate this circle right here, using r and theta, so r is just the radius of the circle, which you already know is root 48, so r is going to go from 0 to root 48, and then what's theta going to go from? 0 to 2 pi. Right, to get the whole circle. So cylindrical, come over, there we go. Okay. Oh, whoops, I shouldn't have put polar, I should have said cylindrical. To cylindrical. Sorry. Okay, cylindrical. All right, so are there any questions? And don't forget you have to put an R in your integrand, right? Any questions on cylindrical? How'd we do with those? Those aren't bad now, right? We're kind of somewhat comfortable. Okay. All right. Let's try spherical. All right. So your spherical. Do I need to walk you through? Or do you want to try it on your own?
No, you want to try it.
You want to try it?
No, what? What?
Wait, will you show us?
No,
You know it's 0 to 2 pi, but what after?
We can figure it out.
I'm going to give you a minute.
Please?
through the.
Oh,
Do you want me to walk you through?
yes,
So,
please,
we
please,
made a guess.
please.
You made a guess?
I didn't know what she did.
We have
What are you doing?
one question.
Oh, you can
Only one? That's pretty good.
Because
Quiet, class. Quiet. There's actually one student who's trying to ask me a question. So yes, Anna, what's your question?
So when you're solving for B,
Uh huh.
and you're using, if you want to use the equation like sine B equals R over P,
Yeah.
and so, oh wait, never mind, I just realized something.
Okay. I'm actually going to show you how I do this. In all honesty, I don't use any of those conversion formulas when I do spherical. Here's what I do. So for spherical coordinates, so the theta is the easiest part because I know I want to go all the way around, right? So my theta is going to go 0 to 2 pi. So theta hasn't changed. So if my theta, I'm done, right? Now all I need to find is my phi and my rho. So rho is whenever you're on a sphere, your rho is a constant on the sphere. So I can generate, I wonder if I should start with the phi. Should I start with the phi first since we go theta, phi, rho? Okay, let's do phi first. Okay, so phi is going to go from 0 to this angle, right? So we have phi equals 0, and we want to go out to phi equals this angle. Does that make sense? Okay, how do I find this angle right here? So that's my phi. So what I do is I just draw myself a quick little kind of a cross section. I draw this little triangle there. I know R. R is root 48. I already found it, right? Now, here's the question of the day. What is this distance right here? It's 4, right? So if this is 4 and this is root 48, can I find this angle? And by the way, root 48, if it helps you to make it faster, root 48 is the same as 4 root 3. Right?
Wait, so the hypotenuse would be 8.
Well, we'll get there. First, we're finding phi, right? So to me, this is just a special right triangle. This is x, 2x, and x root 3. So if this is x, and this is 2x, and this is x root 3, and my phi is opposite the side root 3, then my phi has to be 6e or pi thirds, right? So phi is going from 0 to pi thirds. All right, let's talk rho. You ready for rho?
No, not yet. Wait a bit. I need to process this first.
The upper bound for rho is a piece of cake. What's the upper bound for rho? It's 8. It's a constant of 8. The lower bound for rho, so you got to fill all this space in, right? So we're filling this dome in. Well, we've got the phis, but we need the correct rho. Rho has to go like from this to this. Well, we know the upper boundary for rho is 8 because it's the radius of the sphere, right? So what we need now is a way to calculate rho for a horizontal plane. If only our teacher had given us something to help us calculate rho for a horizontal plane. Oh, right? So the horizontal plane at z equals 4, rho would equal 4 over cosine phi. That's why I did these, is because I spent so long refiguring it out every time, and I finally just made a list and said, like, let's just make a reference. So anyway, so rho is 4 over cosine phi. So, oh wait, let me re-zap these. Okay. So, I think our spherical is hidden to somewhere down there. Where's my spherical? Whoa. Here it is. All right. Okay, so for spherical, here's what I wrote. Yes, well, I guess you could put degrees. I've always used radians. But anyway, for spherical, we're no longer using z for the height of the space. Our theta is 0 to 2 pi. Our phi would go from the y-axis to the angle where the base hits the sphere, which is at, and I wrote out inverse tan root 48/4, but I just did it with special right triangles. Usually it's a special right triangle. So you end up with pi thirds. And then to convert from z to rho, remember that if you do this way, where you like memorize the conversion, so z equals rho cosine phi, so rho equals z over cosine phi, when you have that constant z equals 4, then rho equals 4 over cosine phi. So you're going from 4 over cosine phi to 8, 0 to pi thirds, 0 to 2 pi. Don't forget your integrand is always rho squared sine phi, and then d rho d phi d theta. Yes?
Is there a way to find the upper phi without like drawing that triangle? Is there an equation like?
Oh, so it would be, let's see. So you could do r over rho, arc sine of r over rho, or you could do it's arc tan of r over z. I mean, there's different ways. I always just draw the triangle. I think it's not that hard to draw the triangle. I just draw the triangle. Yeah.
But what if we like don't notice that it's a special right triangle and we just put like?
Then if you have those sides, you can always just do your inverse trig.
You can just do that.
Oh, sure.
I think the same thing. That's what I did.
Oh, okay. And it should have worked, right?
Yeah.
Okay.
Yeah.
So we're going to try one more. It's going to be core in just a minute, but let's just see. Well, we got about 10 minutes. So set up and do not evaluate 3 triple integrals. Again, let's practice rectangular, cylindrical, and spherical. To find the volume of the solid inside both the sphere centered at the origin with a radius of 8 and a cylinder centered at the origin with a radius of 4. So what are you actually finding? You're finding this it's basically like a cylinder with a dome on the top and the bottom, right? So what you get, because it's normally a cylinder, right, has a flat top. Like normally if you just did the cylinder, you would just get, you'd get this cross section. The sphere gives it that nice, like domed top and bottom. Okay? It'll be fun. So you could do this. So yes, I want you to get the practice. Yes, I want you get to do all 3, right? Yeah, good. Okay, so I want you guys to get the practice. So see first if you could do this in rectangular. Try it in rectangular.
So for the rectangular dy would also be a function of the cylinder.
So for the rectangular y would be a function, yes.
Okay.
All right, so let's talk about this personally, just so you know, before we even start. I just checked. I did all of these just with the top half and doubled it. So you can go negative to positive, or you can just go 0 to positive and double it since it's symmetric, right? Okay. All right, so for our rectangular, first if we double it, so first we need the equation of the sphere, right? So the equation of a sphere with radius 8, we all know is x squared plus y squared plus z squared equals 64. So z is plus or minus the square root of 64 minus x squared minus y squared. All right, so you could do your z going negative to positive of those roots, or you could go 0 to positive root and double it. Is everyone comfortable with the z to get from here to here or here to here? Either way. Is everyone okay with the z? All right, let's talk x and y. The x and y, we don't want to do x squared plus y squared equals 64 because that would give us this circle, which is not what we want, right? We want to be inside the cylinder, so we need this circle, right, or any of these circles. So how do I find the equation of that circle? Well, it's the cylinder has a radius of 4, so the equation of that circle would just be x squared plus y squared equals 16. So then y is plus or minus root 16 minus x squared. Does that make sense? Okay. And again, if you wanted to go 0 to that and then double again, you can keep doubling, right? All right. And then your x's would just be, you know, negative 44. So, in all, our rectangular answer looks like that. Oh, I didn't double. I thought for sure I doubled it. Maybe I double it later on. Okay. So our rectangular answer looks like that. Or you could have 0 to the tops and just double. Or if you did 0 to each, 0, 0, 0, 0, all bottom, 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 you could times it by 8. That would take you to the first dot. Are there any questions? How are you guys doing? Yeah? You've already got this and the cylindrical? Good. Okay, so the cylindrical for this is actually pretty straightforward. So your the only difference is your z's have to become 64 minus r squared, right? But they stay the same, just converting. Okay, the theta and the r and theta. So to generate that circle with a radius of 4, you just have r goes from 0 to 4, and theta goes from 0 to 2 pi. Okay, so for our cylindrical, I keep writing polar. I wish I hadn't written polar last year. I wish I'd written cylindrical. Cylindrical. Okay. All right. So 0 to 2 pi, 0 to 4, and then your z's negative positive. How are we on? I think we're getting fairly comfortable. I know we're comfortable with cylindrical. How are we with rectangular? We're all right? Okay. Let's do spherical. Now, spherical is a little tricky on this one. So here's the issue. There are 2 different approaches. There's no way you're going to get this with one integral. Okay?
Okay.
All right. Because if we go out to here, right? So then we would get, so phi would go from 0 to whatever this angle is, and our rho would be a constant of 8, like 0 to 8, right? And that would give us this ice cream cone, all of this in here. But we'd still be missing this part, right?
Let's just forget it exists.
That part's not essential.
We got to add both. So let's do the ice cream cone first. So there's 2 ways. Either you take the ice cream cone and then you add this like funky part that goes around, or you find the ice cream cone. And then the way that I did it that I thought was kind of fun, because I like using spherical to find ice cream cones. It's the easiest thing to find. So if you find the ice cream cone in spherical, and then you can literally just use geometry, subtract the cone, and then add, double the ice cream and add the cylinder.
What?
Lauren's with me, right? Are you with me?
I don't get it.
So what I said was you can use spherical to find the whole ice cream cone, right? And then you use geometry to find the equation of just the cone and just subtract it. and then you're left with just this ice cream, and then you double the ice cream, right? And then you just use geometry and add the cylinder.
Why ice cream? That now.
Can we also just find the
Okay, let's just do it. We're gonna do it the normal way. So we won't do all of that funny stuff. Okay. So we're gonna do it.
I don't want to do it.
Okay, forget that. So we're just gonna find the ice cream cone first, and then we're gonna add the funky space that's around it. Okay.
Alrighty.
All right. So let's find the ice cream cone in spherical first. All right. So we're finding this right here. Okay. So theta, like the theta is easy, right? The theta is just 0 to 2 pi. It's just going all the way around, right? Yes,
So
Jimmy.
why can't you use spherical to find like a cylinder?
You can, but then like if you just oh my gosh, there's the wait. Okay. So you can use spherical to find a cylinder, but the problem is your rho to go out to here, to the edge of the cylinder, it's a different equation than your rho to go to the edge of the sphere. You have different rhos. So that's why you got to have a set of integrals for the sphere part and a set of integrals for the cylinder part. All right? So the part for the cylinder will have its phi from here to here, and the part for the sphere will have its phi from here to here. Okay. So, I know, I'm sorry, it's core. I really want to do this though. Okay, so first thing we got to find is we got to find phi, or phi. So, phi. So, I know this angle, that's my phi. So this length right here is 8, and this distance right here is 4. It's another 30, 60, 90, right? This is x, 2x, this is 4 root 3. This angle, let's see, how do I say this? If this is this angle right here would be a pi thirds for the triangle, which means this angle right here would be a pi 6. So my phi for my ice cream cone is going from 0 to pi 6. Yes, I'd be happy to. All right. So, okay, I have this point right here. To go from the origin to that point, well, that point's on the sphere, right? Yeah. So this radius right here is 8. Okay. To go from the origin to the side of the cylinder, I know is 4. So this little angle right here, I kind of just drew in like a triangle. And I said, oh, well, let's see. If you wanted to find the angle and you didn't know how, like you didn't know your special rights, you could do arc cosine, right, of 4/8, arc cosine of half, and find this. I just think, hey, x, 2x, x root 3. So if this is an x and this is a 2x and this is an x root 3, then this has to be a 60-degree angle. But if you want to just do arc cosine of a half, you're going to get the same thing. But now that's this angle right here. That's not my phi. My phi has to come from the z-axis over. So if this is 60, then my phi is 30, or pi 6, right? So my phi is going from 0 to pi 6. Yes?
And then define the lower bound of rho with the cone. Is it the same thing as the cylinder, or is it different?
So rho, to generate this cone, your rho, anywhere inside of the cone, think of how high you're going, like how far out are you going? Anywhere inside of the cone, you're going from the origin to the sphere. So your rho is a constant going from 0 to 8 for the cone.
The cylinder, it's like the
Cylinder, it's a different thing.
It's like the 8.
Yes, cylinder, we're going to have a funky function.
All right.
All right, that's the cone. I'm almost done, guys, and then I will show you what you're doing for core. All right, so now we got to do this part. Again, what's the theta? 0. Oh, yes.
Sir, before you move on to the other part, do we double the?
Yes, we're doubling everything. Good question. Yes, because I'm only doing top half. Okay. All right. So now to do this part, my theta is still going to go 0 to 2 pi because I'm going all the way around. Okay, we're all okay with theta? Yes? Okay. Phi, well, this was from 0 to pi 6, so now my phi is going to be from here to here. So I'm going to go pi 6 to pi halves. Hey, Josh? Yeah? It's what? Yes. So since my phi for the ice cream cone went from 0 to pi 6, to get the rest of it, I'm going to start at pi 6 and go to pi halves. Like this is pi 6, and then this is pi halves, right? Because we're going from here this way, right? Does that make sense for phi? All right, now it's time to find rho. So I'm going to go back to my nice little reference for side of a cylinder.
Do we get these references on the test?
To be honest, the spherical problem is so easy you won't need these references on the test.
Okay.
Okay. So,
Thank God. It's a sphere.
So a cylinder of radius A has a rho value of A over sine phi. Our cylinder has a radius of 4, right? The sphere was 8, the cylinder was 4. So our rho for our cylinder part is going from 0 to 4 over sine phi. And I doubled everything. And don't forget rho squared sine phi every time for the integrand. Yes.
So like, is the integrand? So the integrand for like the spherical. So that's just by volume then, like for like so it's gonna be like on the. So it's only that you're taking that and integrand.
If you like, this is what you're finding volume.
Yeah.
Yes. So spherical, you're finding volume. In order to find volume, you do your limits. So your theta, your phi, your rho, and then you got to have an integrand of rho squared sine phi. D rho d phi d theta. Yeah. So the question was for the cylinder part. Instead of doubling it, could we have taken our phi from pi 6 to 5 pi 6? And yes, you can. That would also give you the exact same thing. So, yeah. Yes?
So we're kind of finding the cylinder part with the absence of the cones that make up the top of it.
Yes. Yes.
If it was a whole cylinder, then it would just be like 0 to pi over 2.
No, that wouldn't give you a cylinder. You're going to have to get that cylinder. You're going to have to cut off the top and cut off the sides. You're going to have 2 different rows. So you're going to, no matter what, when you've got a cylinder and spherical, you're going to have to do 2 separate sets of intervals. Now, a little note. Notice that since your phi is from the positive z-axis, the biggest phi you'll ever have would be 0 to pi. You'd never go beyond pi because then you're overlapping. So your phi is always 0 to pi. Remember, to get around, that's your theta, right? Theta is what goes this way. Phi is just like a cross section. Okay. All right. Now, I have a couple options for you.
Wait, can you scroll down?
Do you want them on Schoology? It might be helpful. Yes, I will do that. Yes. Yeah.
No.
When I try.
that way to that way.
Yeah, so it's like.
Yes, that would work. Wow, your brain is thinking quite well in 3 minutes. It's like it takes my brain a while to process that, but yes, that would work. Okay, I honestly, mentally would never do that. Like, it's just that's pushing my brain too far. But you're absolutely right though. What Pranav said is, if you didn't want to double the cone, could you take your row from -8 to 8? And yes, you could, because that would give you the cone in both directions with the correct angles. Kind of weird. So anyway, but yes, it would work. All right. So here's what I have for you.